right, so continuing on with our genetics chapter, what we've been talking about so far are what are called monohybrid crosses. Mono meaning one. We've been crossing just one trait at a time. But sometimes you will have a question where they want to know the chances of a combination of traits. For example, let's say that we take two yellow round seed plants that are heterozygous. In other words, they're big R, little r for being round, and they're also big Y, little y for being yellow. So that's two completely separate traits. But what if they said, we want to know if you cross these two parents, what are the chances that their offspring will be yellow and have round seeds? So they're asking for the chance of a particular combination of two traits. So if you understood everything we've covered so far, you already know how to get the chance of round seeds if we just ignored the rest, or the chance of yellow if we just ignored the rest. But now they want to know the chance of both of these things at the same time. So we're going to add another step here. So this is called a dihybrid cross because we're crossing two traits, and they happen to be heterozygous for both of them. We can also have 3 traits, 4 traits, even more than that. So the first way you might solve this, and this may be the way you've solved it freshman year, is using a Punnett square. So let's talk about how we figure out how big a Punnett square is going to actually have to be. We talked about this a little bit last week. If we were just doing one trait, I showed you that a Punnett square, what it's supposed to represent is the possible gametes that a parent can make. But now we're talking about multiple traits. So for example, in this first example, the possible gametes, the way to figure out how many possible gametes is going to be 2 to the power of n, but we're only going to count heterozygous pairs. In other words, if we're big Y, little y, big R, little r, we are randomly going to give, during meiosis, a copy of Y and a copy of R. So it could be big Y with big R, or little y with big R. Notice there's only 2 possibilities. 2 to the power of 1, there's only one heterozygous pair here. So we don't count the R's because there's no choice. When these line up during meiosis, they're going to line up like this, and then the chromosomes are going to separate. We're not going to go through meiosis 1 and meiosis 2, and the options are big Y with big R or little y with big R. It doesn't matter which way the R's line up because there's no choices. We can also figure out the chances of a particular gamete being made. If I said, hey, this is the original gene combination, what are the chances that this parent produces a sperm that has little y, big R? So the easiest way to do this, a little shortcut way, is you can go, well, there's a 1 out of 2 chance of giving little y, right? And then the chance of giving big R is 100%, which is 1 out of 1. So there's a 1 out of 2 chance of getting this combination. In other words, we take each gene and we use the product rule. The chance of giving little y, then look at the chances of giving big R. Let me show you another one. So let's say it's big Y, big R, little r. How many possible outcomes are there this time? Now it's going to be 2 squared. In other words, there are 2 heterozygous pairs. So it's going to be 2 to the power of n. N is 2. That means 2 squared, 4 possible outcomes. Why? Because when this lines up during meiosis, the Y's are going to line up and the R's are going to line up. And what we're saying is it could line up this way, and you get big Y with big R, and you get little y with little r. But it could also line up this way. Now you get little y with big R, or big Y with little r. These are all possible combinations because it's going to randomly give 1 copy of Y and 1 copy of R. So there are 4 combinations here. The more pairs you have that are heterozygous, the more possible combinations. Then if you were asked, what are the chances of giving little y and little r? Then you would do this. Okay, the chance of giving little y, 1/2. The chance of giving little r from this parent, 1/2. So the chance of making a sperm or egg that has this particular combination would be 1/4. Okay. So let's try these 3 practice problems. So how many gamete combinations are possible for this parent? All right, so for the A's, they're not heterozygous. Remember, the formula is going to be 2 to the n. N is just going to represent heterozygous pairs. So A is not heterozygous. There are only 2 heterozygous pairs, so it's going to be 2 squared, or 4 possible combinations. Now, what are the 4 possible combinations? So I'm not going to write them all out, but we can figure out the possibility of making any particular one of them. So let's look at the first one. What are the chances of making big A, big B, big C? Well, the chance of big A is just 1 because they only have big A. The chance of making big B is 1 out of 2 because in meiosis, there's a 1/2 chance of big B and a 1/2 chance of little b. And the chance of big C is also 1 out of 2. So the chance of making this particular gene combination is going to be 1/4. What about little a, little b, little c? This is a trick question. Notice that the parent is big A, big A. So the chance of making little a in a sperm or egg is it's not possible. So your whole answer just becomes 0. So going back to figuring out how big a Punnett square would have to be, you can only use this, what I was doing with the 1/2 and all that, you can only use that to figure out chances of a particular sperm or egg. You cannot use that to combine 2 parents. Be very careful about that. If you try to combine 2 parents and use this method, you will not get the right answer. You have to use Punnett squares to figure out the individual traits. You'll see what I mean in a second. So anyway, so let's see, how big would a Punnett square actually have to be? Well, you use the 2 to the n, so we just said that this one had 4 possible combinations. This one also has 2 squared, 4 combinations, so you would have to make a 4x4 Punnett square. In other words, across the top, you'd have to have all the possible combinations for the first parent. So big A with big B with big C. It could also give big A with little b with big C. It could also give, and you'd have to write out every possible combination for the first parent. Then down the side, you'd have to write out every possible combination for the second parent. You would have to have 3 letters above each box, and then inside the box, you'd end up with 6 letters again. Because we're representing meiosis and then fertilization, all the possible babies inside the boxes. This throws a lot of people off, which is why I'm going to show you a way to solve this without using a Punnett square. So back to our original cross, the question was asked, what are the chances of yellow and round from 2 heterozygous parents? So you would need a 4x4 Punnett square because this parent can make 2 to the n, 2 heterozygous pairs, 4 possible combinations, and you'd have to list all 4 of them. The other parent can make the same 4 combinations. You'd have to list all 4 of them. Then you'd have to put the letters back together in the boxes and then physically count how many will be yellow and round. So if you do that, this is actually a very common cross. You can memorize the outcome of this cross. You would expect a 9:3 to 3:1 ratio, meaning out of 16 offspring, we would expect 9 out of 16 to be dominant for both traits. This dash means that the second letter doesn't matter. It doesn't mean they don't have a second letter. It means that the second letter could be big or little, they're still going to be yellow. So there'll be 9/16 dominant for both traits. We would expect 3/16 dominant for the first trait, recessive for the second. 3 out of the 16 recessive for the first, dominant for the second, and the last 1/16 recessive for everything. Now, this is a lot of work to try to figure out. So there is a workaround for this. And the workaround is to use the product rule. Look at how big this would have to be. If you had this cross, where they were heterozygous for 3 traits, 2 to the 3rd power, that's 8 possibilities. You'd have to come up with what the 8 possibilities were for each parent and write those above the boxes. This is the gametes, after meiosis, the haploids. In the boxes, you'd have to put it all back together again. And it would be 64 boxes. That's ridiculous. There's no way you're going to have time to do something like that. So you can use the product rule. This is going to actually be much faster. Remember, the chance of any 2 events both happening is the product of their individual chances. So if we do the crosses individually, here's what we'll get. So if we cross big R, big Y with big R, big Y, little y, we can just cross the R's, so we're separating out the traits. So if we just cross the R's over here, we are going to get a 3/4 chance of round and a 1/4 chance of wrinkles. And then for the yellow versus green, we're going to do big Y, little y, big Y, little y. Same thing. We're going to get a 3/4 chance of yellow and a 1/4 chance of green. So our original question was, what are the chances of yellow and round? Well, the chance of round is 3/4 times the chance of yellow is also 3/4. That gives us 9/16. So you could work out all the possible outcomes and you're going to get the exact same answer you got with the giant Punnett square, but without having to make a giant Punnett square. Okay, sorry, it's my little work here. So here's 5 practice problems. So here's the first one. What are the chances of these two parents making a child that's this combination? So I'm going to do this very quickly. If we cross our A's, the chance of big A is 1/2. Now we're going to cross our B's, big B, little b, with little b, little b. The chance of big B, little b is 1/2. Times, if we cross our C's, this is big, little, the chance of little c is 1/4. So that's going to give us a 1/16 chance of that particular combination. Let's try the second one. So we cross our T's. The chance of tall is 3/4. We cross our B's. The chance of black is also 3/4. And finally, we cross our H's. The chance of hairless is 1/2. So 3/4 times 3/4 times 1/2 gives us 9/32. Notice how fast we can solve that rather than trying to make a Punnett square. If you tried to make a Punnett square, this would have to be 8 by 4. So a 32 box Punnett square, and you'd have to put 3 letters over each box. This last one is a trick question, I believe, because you can't get big H, big H. This is just 0, because this parent is little h, little h. Okay, for this one, it is actually just as fast to do a Punnett square, so I'll show you this one really quick. So this parent can make big T with little b and little t with little b. This parent can make little t with big B and little t with little b. Again, this tends to throw some people off because they really have a hard time wrapping their head around putting multiple letters above the boxes. But remember, it's 2 traits, so we are representing each trait with a letter here. So little, little, big, little, and then little, 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 little. So we get a 1/4 chance of tall black, a 1/4 chance of short black, a 1/4 chance of tall white, and a 1/4 chance of short white. If you do it with the product rule, you'd have to get the chance of tall and short, and then the chance of black and white, and then you'd have to multiply the individual chances together. You will get the same answer, but honestly, if you understand how to make the Punnett square, that one is actually faster if you just put it into a Punnett square. This last one would only be bonus on your test. I'm not going to have time to run through this one, but this one you would need to use the addition rule. There is a workaround I showed in class, but if you want help with how to do one like this, I'll be glad to show you in class.